Why lead used to gasoline? Okay. What's the number rating? That's octane. Or I should say is originally octane, and then it becomes a performance number. Because we can have higher than 100% now, right? We can have 110 or 120. You may see fuel octane ratings. You may see something like this. It'll have an octane rating of 100/120. Okay. That's a lean and a rich side. But we normally only just talk about the lean one if there's only one number. What's the advantage of high octane over low octane? Well, increases detonation. That's what octane means, right? Its ability to resist detonation. What is adding lead to gasoline? Well, it does that job. Why do we no longer use it? Lead poisoning, environmental effects. Okay. They used to call it loony gas because it made people crazy. Okay. Kills brain cells, makes people more violent, bad for the environment. Okay, watch volatility of chemicals. What would have happened for this demonstration if a fuel with a low volatility such as kerosene was used? I don't really know what that is. We'll skip that one for now. It's just for fun. What is airlock, vapor lock? What are the source of vapors in a fuel system? Yeah, we could say the source is heat, possibly. Heat or ambient pressure. How would using a fuel with low vapor pressure reduce this problem? Well, it's less likely to boil, right? Or evaporate. Why not use fuel with a lower vapor pressure? We do. Leaded fuel. Right? How about our avgas? How would allowing fuel to get hot make this problem worse? Well, it evaporates faster. How would avoiding bends, kinks, high points prevent? If we have like a kink in a line, okay, the air bubbles can get trapped in there. And if that air bubbles gets big enough, it can actually create a blockage. Okay, vapor lock is when we have like an air bubble inside a line. This fuel pressure wants to come in here, but it's blocked by this air bubble. This air bubble gets compressed, causes all sorts of problems. How does boost pumps reduce vapor lock? Well, it increases the pressure in the system. Stoichiometric ratio, chemically balanced, 14.7 to 1. by weight. Right, so we burn a chemically balanced, and we're going to be using up all the fuel and all the oxygen in that chemical process. No leftover parts. Okay, there's the number. Does it change with altitude or temperature? Yes, it does. Right? 14.7 parts of air. Actually, if it's by weight, it wouldn't change. You'll just need a lot more of the air. When's the fuel air mixture the richest? The richest at idle. When's it the leanest? Cruise, right? We want best fuel economy. Repeat the last one. Does it change with altitude or temperature? Well, this stoichiometric ratio is 14.7 parts air to 1 part fuel by weight. So the ratio is always going to be the same. Stoichiometric is stoichiometric. So it's an unchanged number. But as we get higher in the atmosphere, we're going to have to adjust our mixture because our density is less, right? So we're still trying to get our certain ratio. I mean, ideally we want 12 to 1 for best power. But we want to lean it out. We even want to lean it out kind of further than stoichiometric. Right, for the best fuel economy. What happens if 2 lean mixture is delivered to the cylinder, and why? Well, what's associated with lean? You get a slow burn, slow and hot, right? If it's too lean, hot can give us detonation. And slow, we have the possibility of backfiring. Why is an accelerated system needed? Captain Fast, right? He wants to move that throttle up really quickly. And we have that instantaneous change in air pressures, but the fuel is more dense, so it's slower. So we need something to compensate for that engine stumble that we'd run into. Why does airflow increase faster? Because it's less dense. What would happen if there's no accelerator system? We'd have engine stumble. In a worst case scenario, it could kill our engine if the stumble's bad enough. Well, because we fly in the atmosphere, right? That's why we need mixture control. What would happen if we had no mixture control? What happens when we go higher in the atmosphere? Does it get more lean or more rich? As we go up, air is less dense. Right? Less dense as we go up. And if the fuel stays the same, what's happening to our ratio? going to get too rich. How is a mixture control actuated from the cockpit? With the mixture control, right? One with the red handled star looking one is our mixture control. Why do aircraft engines use fuel cutoff to stop the engine? Why not ignition? Does anyone know that one? Yeah, you don't kill someone. It's a safety feature. Because we have impulse couplings. If you remember from the magnetos, all we need to do is turn that propeller and we create ignition. We don't even need a battery. But more so than that, by killing the fuel, there's no residual fuel in the system. Okay? If we just shut off with ignition, which some pilots do, there's still fuel in the fuel manifold if it's carbureted. Okay? If the engine's off, the aircraft's off, the pilot's out of the aircraft, but they shut down with the ignition system, there's still fuel in the intake manifold. And if someone bumps that propeller and the impulse coupling fires, that propeller can kick over, maybe just like one rotation, but the force involved is enough to kill someone. Yeah, it wouldn't necessarily start. It might momentarily start, but I mean, some of these engines have hundreds of horsepower, right? Hundreds and hundreds. So that even in an instant can kill us. Safety. How is idle fuel cutoff activated from the cockpit? We bring that mixture control all the way back until there's no more fuel going to our engine. Okay, what's surface tension? That's like a liquid's characteristic to stick together. Okay, remember like the glass of water? We fill it to the top and it forms a meniscus above the edge of the glass. Or remember those water bugs, right? They're so light that they only kind of put a little dent in the water. Surface tension is not broken. Does the air bleed help in fuel vaporization? Of course it does. That's what it's there for, right? We introduce air bubbles to help break up the surface tension of the water, of the fuel. Does the idle system use an air bleed? Yes, it does in a float type carburetor. No, it doesn't in the pressure carburetor. How does the idle system work? Does it depend on Venturi? No, it doesn't depend on Venturi. It depends on the difference between manifold pressure and, I'm just going to call this upper deck. Right, we have those little port sensing the difference. The pressure differential across there is larger than, because we don't have much airflow going through the Venturi, so the sense for that is not great enough to draw fuel out the main nozzle. Right. Surface tension is a liquid's ability not to be broken. That's correct. No, not dependent on the Venturi. How is it adjusted? Idle system. Well, we have our idle mixture adjustment, and we have our idle speed adjustment. Stop that we can adjust on the throttle linkage. Why are float carburetors very susceptible to icing? Well, because we're using the low pressure to draw the fuel out here, what comes with low pressure is low temperature. And also as the fuel is evaporating, remember that also cools the fuel down. So those two combinations here in the right circumstances can cause icing. Pressure carb, remember we have that other main discharge nozzle up on the other side. There's still a Venturi, so there's the low temperatures there, but we're not dealing with the fuel evaporation cooling. So they separate those problems, make it less likely to have carburetor icing. Outer pressure, okay, yeah, I talked about that. Is the fuel injected upstream or downstream of the Venturi and throttle plate? Okay, there's upstream and downstream. Our stream's going this way. This is the upstream sound side. This is the downstream side. Right, so fuel injected, we don't even inject it till right before the cylinder. So way downstream of the Venturi and throttle plate for fuel injection. How are we doing here? Do we need a break or keep on going? Break. 5-minute break. 5-minute break, yes or no? Every vote counts. Well, it looks like we're going to take a 5-minute break. Okay, let's come back at, let's take a 4-minute break. 10:50. And we're back. Quick little break. Okay, we're talking about pressure carbs now. How does an increase in airflow cause an increase in fuel flow? All because of the air metering force, right? Difference between Venturi suction and impact air. Acting on the diaphragm and poppet valve. Where is the chamber on the low pressure side with the diaphragm connected?
Stay on my paper shit. Act like you can't tell who made this new gospel. Homie, take 6 and take this. Haters.
In the real pressure carburetor, where is the chamber on the high pressure side of the diaphragm A connecting? Where's the chamber connected to? Well, normally you'll see impact tubes sticking out. What pressure pushes back against the air metering force? Regulated fuel pressure, right? Air metering force opens the poppet valve, and the fuel metering, the regulated fuel pressure pushes back against that. Low pressure in through the venturi. In through the venturi, it makes its way to chamber B. Impact air makes its way to chamber A. You good, Andy? I'm lost. I don't know where we are. We just started reviewing pressure carbs. Lost you after air metering. Okay, we'll back up a bit. So we'll go back to this one. How does an increase in airflow cause an increase in fuel flow? Well, that's the difference of negative venturi pressure and positive impact pressure. Okay. Negative in there, positive in there. That makes this whole unit want to move to the left. No, sorry, to the right. Which opens that valve. Remember, that valve sits in an area like this, and it kind of looks like this. Okay, so as we move this way, it's unseating, increasing the gap between the valve and the seat, letting more fuel into the system. More difference of air pressure, more fuel. Okay, is there a float chamber anywhere on the pressure carburetor now? How does this help an aerobatic flight? Well, it doesn't have any effect because we don't have to worry about it. Okay, what happens if we turn our float chamber upside down on a float carburetor, right? Let's turn everything upside down here. We got fuel supposed to be coming in there, but now our float from gravity is keeping this closed. Also, now our fuel's upside down here. Okay, some might just pour out too much, or maybe not enough if the fuel's in the wrong spot. So it'd be very inconsistent if we're upside down or doing abrupt maneuvers. Okay, maybe the fluid's in like this if we're making a hard G-force bank. Okay, what's going to happen there? Now we have no fuel coming out. Our engine's going to die. So float type carburetor is not good for aerobatics. Does the idle system have a separate fuel discharge like a float carburetor? Nope. Right, here's our idle valve. There's no separate idle emulsion tube like in the float carburetor. Our emulsification all happens at the discharge nozzle. How's idle speed adjusted? Idle stop screw. Just like the other systems. Locate the throttle body. Okay. This whole thing is the throttle body. Right, that whole housing. Right, so all this gray, this whole thing is called the throttle body. It's a body that houses the throttle. What atmospheric changes do aneroid bellows respond to? Pressure and temperature, right? How would a change in temperature affect the fuel-air mixture? Well, the hotter things get, the less dense they are, the less dense the air pressure is. The higher we go in the atmosphere, it's less dense, but if we make it cool, it's going to become more dense. Right, so here's the temperature pressure chart. Sea level 29.92 inches of mercury, 14.7 psi, 15 degrees Celsius. That's our standard day sea level. As we get higher in the atmosphere, temperature decreases. Our pressure also decreases. The air temperature does stabilize around 35,332 feet though, for a while. Okay, how are fine adjustments made on the float height? There's that little tang. Okay, so we have the part with like the hinge on it. Right, then we have a little tang in there. If we're looking at a side view, that little tang is up a little bit. We can adjust that up and down. Some of you haven't even got to the float, the carburetor project yet. But these are connected to the floats. Okay. And on this little tang here, we connect the needle seat. So by moving this up and down, we change the location of where these floats sit. Where's the needle seat? And what actuates it? The floats actuate it. The needle and seat. Where is it here? Here it is there, the needle and seat connected to our floats. Not shown in this one. There's a good picture. That adjustment tang is right in there. Wrong color. The adjustment tang's right in there. What would happen to the fuel level in the float bowl if the float were to sink? If this float sinks, it's going to bring this needle valve down. Fuel's going to come pouring in here, and since the float's not doing its job, the fuel level is going to keep going up to the very top of the carburetor. Where can it go? Well, we got the main nozzle in there somewhere. It's going to eventually just pour out of there until we have no more fuel left in our fuel tanks. This float sinking is not even a problem nowadays because we use advanced polymer design. So even if you drill a hole in it, it'll still float. If the float is in good condition and adjusted properly, what will happen to the float and fuel level in the float bowl as the engine power level increases? Well, we're going to have a bigger demand of fuel, so the floats are going to drop a little bit and let more fuel in. Okay, the float and needle seat and valve always maintain a specific height, no matter what our demand for our engine is. What is volatility and how is it measured? Volatility is a fuel's characteristic to evaporate. And how's it measured? Read vapor pressure. How are the different grades of aviation fuel identified? Color. We got red, green, blue, and if we get into diesels or kerosene-based ones, jet fuels, for like a straw color. Straw is like very light brown color. What color is 100 low lead? Blue. How is fueling equipment marked? With 100 low lead. Okay, 100 LL. Those stickers that go in the fuel tanks, on top of the wings, for example. We fill them up on the wings. The stickers on there, or the decals, will tell you the fuel type and fuel quantity of each tank. If those decals are illegible, this airplane is not supposed to fly. Yeah, they just add dye into the fuel just to help us identify it. The dye doesn't give us any performance characteristics. It is helpful for finding fuel leaks. Let's say we have those little fuel water drains in the bottom of the wing to check for water. If one of those is leaking, you'll see like a blue staining around the leak. Okay, or any type of leak. You might see fuel leaking on the side of the fuselage. But as the fuel, because it's such a volatile fuel, avgas, it evaporates very quickly. So the fuel evaporates, but the dye is left behind. So it's very helpful for troubleshooting leaks. Why is it that gasoline vapors can cause a hazard far from their source? Well, if we got a barrel of fuel here, remember the fuel vapors are heavier than air. So they kind of pour out. We can't really see them unless it's like a hot day. But they collect on the ground and they can travel. They can travel to other places. And that makes it dangerous because we can't really see it. We can't really smell it because it's, our schnoz is up here, right? It's kind of like that mirage. I guess you could see it on a cold day, but on a hot day, it's going to evaporate faster and you can see like the wavy lines of it evaporating. On a cold day, it's not going to evaporate as quickly, so you're not going to see those wavy lines. So it's easy. Yeah, the vapors travel on the ground. How do we prevent static friction from flowing gasoline from causing a spark? Well, if we're pumping some gas in there, our fuel truck, we ground it out. We ground the airframe out. Well, we actually do that by pushing the metal fuel nozzle against the side of the wing fuselage, not the fuselage, but the wing frame. So that gets grounded out. And then we're going to ground out the aircraft to the ground as well. So that any type of static electricity that does build up from the fluid going through the hose will get grounded out one way or the other. Yeah, Vincent, the vapors, they're heavier than air, so they travel. They just want to space out. Travel on ground. My writing's getting pretty messy today. If fuel is stored indoors, what precautions must be taken? Flame resistant. Cabinets. What else do we have to do? We need a fire extinguisher. More than 3 meters away, right? If it's too close, we'll be trying to get to our fire extinguisher and burn it up. How do we prevent static again? Yeah, grounding equipment and airplane. AP, when refueling, static is prevented by a ground wire attached to an aircraft. But when storing or other items, no idea. Well, if it's stored, then it's not moving around, and that static electricity is not going to build up. If we're storing barrels, we want to store them on their side. Okay, with the bungs kind of in level with the ground. Because if we look at the top of a big fuel barrel, it has a lip on the edge. And we got the bungs in there. Big bung and a small bung. Fit in the bung holes. And we can get some rain or water in there. And if our seal's not so great on our bungs, we can get water getting mixed into the fuel, which is no good. Okay, that's the next question. What concerns are there using automotive fuel? More susceptible to vapor lock, right? They have a lower, or is it a higher read pressure? Why does it do that? Okay, automotive fuel more susceptible to vapor lock. It's not designed to go high in the atmosphere. Avgas is. What problems do alcohol blended fuels cause? Well, blended is kind of the key word here, right? We mix alcohol in there to boost our octane rating, but if they separate, alcohol is hydroscopic, which means it attracts water. Water wants to get in and mix with the alcohol. When they separate, our octane level is gonna hydroscopic means the alcohol attracts the water, right? Kind of sticks to the water and takes the alcohol out of the blend, effectively lowering our octane rating. And if we have too low an octane rating, we're going to be more susceptible to detonation. When we have that alcohol-water mixture, it also creates acids in there, right, which can cause corrosion. Son of a gun. Oh, that's it. It's less volatile, so it doesn't evaporate as easy. So these vapors on an avgas barrel evaporate much easier. And we know that we need a fuel to vaporize in order to burn it. So more susceptible, meaning it evaporates easier and evaporated gas burns. And also just working with avgas in general, because it's leaded, it's toxic to us. So always put some gloves on if you're working with fuels. Any type of fuel. Jet fuel, just because it stinks bad. What separates the chambers in a regulator unit? The rubber diaphragm. Let me see if I have some pictures for you. The pump. That's all I got for that. No, I don't have a picture of a diaphragm. Can you show me the chambers on the low pressure diaphragm is connected and high pressure side. Can you hear me? Hello, check, check, 1 2 1 2. Suk, can you hear me? Can't hear me. Turn your volume up. Did you try unplugging and then replugging it in? Okay. What else can I help you with review? Let's see what we're dealing with here. Content, student resources, what's in the study guide? Hopefully you still know about this little gem. We are doing E2, right? So we're talking about fuels, float type, and pressure carburetors. E2 practical project. Okay, some of you haven't even started this. Have you started the P2 project? Yes or no? Okay, well, there's a bunch of you who haven't. So, what's P2? Yeah. Oh, that's right. We are only doing oral portion of that project for now. So there's some test questions based off of you doing the practical project, but it'd be questions like, how do you adjust the floats? We talked about that in our lecture. Right about here, right? We turned it upside down. We put the twist drill in there to set the proper float height. The twist drill is just used as a convenient dimension that's requested. We're adjusting that little metal tang here, okay, to adjust the float height. When we're done, we're doing things like this. We take the drain plug out, attach a sight tube. We put some test fluid in there to simulate fuel to see that a certain height is reached and maintained. If our needle valve and seat is leaking, this tube would fill up and overflow, and we could see very easily. Yeah, Andy, P2's oral only at this point, yeah. But if you think there's a question on there that you had no chance of seeing, I'd fill out a blue sheet at the test center to let me and Mr. Lazarus know, and we may just give you a free mark just because of the things of how they've worked out. Okay, we've got the FAA Chapter 2. We even tell you exactly what pages to look at. H1 handout, H2 handout, and Tips on Engine Care. That's that book from the library. Quizzes. 60-minute quiz. Okay, it's probably 30-something questions long. Oops. Don't look there. Let's get rid of that actually. Preview. Let's preview it. Yeah. Well, I don't see any cash money in my hand. These things aren't for free. Cash money. How much you got? AMC shares, those things are going to be. Is those worth anything? I thought you're not supposed to sell those things. Get in, now you're talking. A quad? No thanks. What am I going to do with the quad? No, I didn't say done for today. Okay, let's see what we got. $10 free flights on the air carrier destination. That sounds pretty good. Okay, so what's due? We had P3 and P7 due yesterday. Friday, everything's due, right? It's the last day of class. P1, carburetor workbook. P2, oral only. P5. Mr. Lazarus is heading in today. He's doing some marking so we can give you some feedback for your P7 on Friday. Friday is going to be a wrap-up day, finish our projects, and a class cleanup.